So, well there, welcome back. So, you have started watching videos on mathematical foundation of robotics, and we are discussing execution level control. You see, in the name of background creation, we are, with some detail, we are studying second order system, and this is very, very important actually, in vibration and control, in understanding in mechanical system, or in electronic system or electrical engineering. This second order system is very, very useful for various applications, including um, the control, okay, creation of background of control. You see the mechanical example which you have taken with the in the form of mass spring damper system. The same mathematics, same techniques can be applied in an electrical analogy with RLC circuit, okay, RLC. So the behavior of this RLC circuit will be same RL, so resistance, capacitance, inductance and capacitance. So resistance, inductance, capacitance, and this is an EMF generator. And if we just perturb means this is a battery or EMF creator, we just touch the two ends and leave it. And then what will be the behavior of the current with respect to time? That is all we wanted to know. Okay, and behavior of current with respect to time, and the x with in case of electrical signal, or in case of mechanical model, that is MCK, the x versus t, it will be exactly same. Okay, so that's the beauty, right? So we are studying quite generic model of a second order system. Now let us continue our discussion. So just recap that this is our using D'Alembert principle. So this is what your free body diagram is, and then we are making a trial solution because solving a differential equation is difficult, and we have few methods for solving that, and that's why any of the methods can be useful, not everywhere, right? So that's why there are so many methods. So here, for compact solution creation, we have used x equals to a to the power st the other day, and then we have solved. We have transformed the differential domain equation from the differential domain to the algebraic domain. Okay, where second order system means a quadratic equation. Isn't it great? And then the roots of the quadratic equations are given by this in terms of system parameter. That is, C is the damping coefficient here, okay, and M is the mass of the system, and then K is the spring stiffness. So every parameters are known to you by this time, and then you have the two roots. Okay, two roots means two solutions, right? So this is the second order system. So you have quadratic equation, characteristic equation is quadratic, and you have two roots. And since the second order system is a linear one, I can compute the total solution by simply adding them, these two roots, because the principle of superposition holds good if the system is linear. So, and I wanted, for mathematical convenience, I wanted to express this in terms of a dimensionless parameter. In engineering, you have always done this in design also. So here, they have advantages, right? Here, they are very compact. So that's why we have introduced a dimensionless parameter zeta, and we have defined it like this. Zeta is damping coefficient divided by damping coefficient at critically damped condition. What is critically damped condition? When C by 2m equals to K by M. C by 2m square equals to K by M. Sorry, C by 2m square equal to K by M. That is the quantity under the discrimination under this root becomes 0. So that is critical damping condition, which we have noted it here. and this is what critical damp coefficient is. Okay, so zeta is defined like this, C by Cc, and in terms of zeta and omega, C by 2m equals to zeta omega. Okay, and then we can, yes, that's the reason we have introduced this parameter, right? We can write x equals to a1 e to the power minus zeta plus root over of zeta square minus 1 whole into omega t plus a2. These are the two constants associated with each root. Okay, and then we have discussed three different situations, right? One is called under damping, over damping, and critically damping condition, right? So case 1 was actually when zeta greater than 1, that is C by 2m greater than root over of k by m. And so this is called overdamped situation. Okay, so it will be non-oscillatory in nature, and the roots will be, this will be, because you see, very interesting observation, zeta square minus 1 under the discrimination root less than zeta. So you see, you have a solution which is a1, some constant, e to the power minus zeta plus something which is less than minus zeta. So this is negative definite, right? E to the power something negative plus a2 e to the power something big negative, because minus zeta is negative, and minus this is again less than zeta. So you see, so always, that's the beauty, always that if we now we'll see, if we plot them in S-plane, S-plane, you know, this is your real axis, this is your imaginary axis. So roots are always, will always lie here, always, okay, in such model. Okay, so as long as this is positive, okay, roots will always lie in a second order system, second order mass spin damper system, always lie in the negative domain, which ensures that if I can design a controller with such root, where the root will be always traveling somewhere here, and I will design the gain parameter, then I can prove that my controller is stable, asymptotically stable. Okay, so there's nothing to be worried. Means controller stable means controller will lead to my objective. Where I want controller to take my robot, controller will take there for definite. Okay. Now there is another situation when zeta less than 1. That is called underdamped system. And you see, and then you see this becomes, so zeta less than 1, this becomes negative. So negative definite. So that's why we introduced a term I, which is equals to root over of I equals to root over of minus 1. And then I have written like this for mathematical convenience. So, and then it can be proved that the x will be oscillatory in nature. Okay, but also we have proved that what type of oscillation will be there? The oscillation will die down, and oscillation will be within this envelope, because we have actually optimized it, maximum and minimum. So we have seen that x equals to root over 1 minus zeta square x e to the power this, and plus, and this minus. Okay, so this is a simple reduction which we have done in my last class. And another one was actually critically damped situation. When it is critically damped situation, that is zeta equals to 1, that is c by 2m equals to root over of k by m. So somehow some clean deduction I have given it here, that when omega d tends to 0, sine omega dt tends towards omega dt, and cos omega dt tends towards 1, and that's why you are getting 2 constant. So it's a general solution. Otherwise, from here only you can get a general, somehow general solution, which is important. Otherwise it was difficult to get a general solution. Okay, just simply in my earlier lecture you have seen, just by simply putting zeta equals to 1, here will create some 2 constant. Okay, and two constants, sum is another two constant is another constant. So it was not a general solution because second order system must have two constant, arbitrary constant whose values would be determined using boundary condition or initial condition. And just I have shown you that this is critically damped situation. So if I try to plot all three in one plot, then it will be overdamped. This is underdamped. And this is critically damped. Situation, okay? So, with this, so those deductions we have made, that means study we have made when mass spring damper system only perturbed. That means there was no external excitation continuously, okay? So instead, there was perturbation, and that's the way it will behave. Now what if, just like earlier mass spring system with external excitation, if my mass spring damper system is always excited by an external agency, right? This is P versus T, P equals to P0 sine omega f t. Suppose this is a force which is actually continuously sinusoidal force. Force could be anything actually. Sinusoidal force, if it is actually acting, then what will be the nature of the solution, right? It's very easy. Again, instead of putting 0 here, this will be the force, right? So again, there will be two solutions, one x equals to xa plus xb. Xa is complementary solution or transient state solution. Sometimes it is called complementary function. And xb is particular solution or steady state solution. In control terminology, it is very interesting. This is called transient state solution or transient state response. And another one is steady state solution or steady state response of the system. So again, I will not go into detail. The solutions I am directly writing. You take a notebook and exactly the way the earlier lecture we have already reduced it. So you just reproduce it. Okay. This is for zeta less than 1. This is the solution because since it is sinusoidal, right? We are interested to know the solution which is sinusoidal in nature, right? So this one and this amplitude oscillation, damped oscillation, and this is how the oscillation will take place. So this is our, here, we have already, so this is already we have, this is corresponding to 0 or transient state response. We will be following this. Now another solution will be like this, m is a constant, n is another constant. There has to be two constants because it is a second order system, and we are assuming that the solution will be something like m sine omega f t plus n cosine omega f t. So if this is a trial solution, again trial, this is a trial solution, it must satisfy this. So the expressions are extremely simple. You need a copy, pen, but it is extremely simple, but it is a little bit lengthy, laborious, because a lot of ugly terms will be there, but they are very simple, isn't it? You just differentiate it, double differentiate it, put it here, and then just try to figure out what will be the xb, okay, in terms of known quantity P0, x, c, m. So these are the known quantity, and omega f. Omega f is known because this is the circular frequency of externally excited force. So this is known, this is known, this, because the system is known, these are parameters which are known. So in terms of those parameters, I have skipped this for you. This is an assignment. X will be equal to P0 divided by K under root K minus M omega square whole divided by K square plus bracket C omega F divided by K bracket close square. So in terms of, I wanted to express everything in terms of R and zeta. So this is very interesting. So you can just put them in terms of R and, so this is x naught, and then 1 minus see m by k, so omega squared divided by m by x squared, that is omega squared, that is r. R is the omega by omega f, right? So this is the frequency ratio, this is dimensionless parameter, zeta is dimensionless parameter. So everywhere you see you have we have done this, right? R is actually R is defined as here, no? Wait a minute. I have defined R omega f by omega, right? R equal to omega f divided by omega. Okay? That is frequency ratio. It's simple, right? So one I can show you 1 minus omega f divided by omega square. So 1 minus r square. Okay? 1 minus r square whole square, right? So this is this expression. So this is equals to frequency ratio called r. Okay. So you have got this. Then we are actually defining another dimensionless parameter quantity, magnification factor. Okay, magnification factor, which is defined nothing actually. This is the expression. I am just simplifying because I would like to study the characteristic feature. So x divided by x0, 1 by this. This is dimensionless parameter. This is dimensionless parameter. So if I draw the characteristic feature which I have drawn here, okay, you see, this will be universal because all dimensionless parameter, right? Similar, everywhere you will see similar kind of characteristic. Now see what is that characteristic. R equals to 1, that means your natural frequency is equals to the external frequency, okay? So, and if zeta is 0, zeta is 0 means no damping, so this is 0. So again it is mass spring system with external frequency matching with system natural frequency. You know what will happen. The magnification factor will be infinitely large. The amplitude of oscillation will be infinitely large, which we call resonance, right? So if R equals to 1 and zeta damping factor equal to 0, then there will be resonance. Then we damp actually system. More damping is there. So the magnification factor versus R, if you draw the characteristic curve, it will be like this. So these are under damped condition, no damped, under damped situation, critically damped situation. Then you can actually over damped situation also you can plot. Okay. Okay. Over damped situation also you can plot like this. Whatever. Okay. So this is critical. This is the characteristic feature of x by x naught versus r. Another parameter we have, you know, here, this is psi. Psi is the phase. That is also you can, using separation of variable principle, you can do that. C omega f divided by k m omega square. So again, divided by k, same old story. We are expressing tan psi in terms of two dimensionless parameter. 2 zeta r divided by 1 minus r square. And if I plot tan psi, you see, this is psi. So if I plot tan psi, then the plot will be like this. You see, it at 180 degree, it will be asymptote, and then as you see, the phase drastically changes at pi by 2. Okay, so this is what will happen. Interesting curve. Okay, and this is for critically damped situation, and these are for under damped situation. So this characteristic and this characteristic, very interesting characteristics, you will come across in many control and second order system analysis, right? Now, having understood the second order system with fairly with sufficient details, now we are able to appreciate its utilization in control. Suppose a system is excited by a step function. Unlike this system, mass spring damper system is excited by a step function. Then suppose this is actually characteristic equation, a square plus 9s plus 9 equal to 0. So minus square minus 36, right, by 2, and whatever you just see. And so situation is actually overdamped situation, and the roots will be negative definite, and they will be on the negative on the real axis. They are real, always negative, so they will lie on this axis, real axis. So this is S-plane or argon diagram, as you can call it, many names. So here we can plot real axis and imaginary axis orthogonal to each other. We can plot the roots of the second order system, and or we can call them pole in control terminology. Okay, so the roots are here, and since you can appreciate e to the power minus something plus e to the power minus something, so there will be no oscillations, only asymptotically, exponentially they will reach towards 1. Okay, so there are two kinds of solution. No? I told you that complementary solution or transient state solution, which is when this is equals to 0. So and then there will be particular solution or steady state solution. So since in the steady state the step excitation is always there, it will try, that is the only implication, right, understanding. It will try to achieve that in the steady state. So this is called transient state. Okay, from here to here, transient state. So this time is called settling time, but ultimately overdamped means after some time, considerable amount of settling time, it will asymptotically reach towards 1. Now let us see another. So this is step input. So this is input, this is transfer function, and this is the output, what you are getting. So output you are getting like this. And what if the transfer function, the denominator of the transfer function is a square plus 2s plus 9 equal to 0. Then you can see the roots are imaginary, they are complementary, but they are negative definite. Why? I already told you that minus something plus something which is less than this, which is minus something minus something which is big minus, although there is item, but that I only will determine where will be the location of the roots. Okay, so they are having imaginary part, so that means the roots have imaginary part, means there will be oscillation. So this is called underdamped system, and you see this is the response. So what you are observing? So this is called transient state. So some oscillations here and there, and then ultimately it will stabilize. That is the proof, because e to the power minus something is there, and due to the presence of I, e to the power I theta equal to cos theta, Euler's equation. Due to the presence of I, there will be sinusoidal, little bit sinusoidal oscillation, but oscillations are damped oscillation. You have seen in my earlier lecture when we detailed studied about the second mass spring damper system with perturbation. There we have shown that it will be damped oscillation, means the amplitude of oscillations will decay over time, and it will, and jokingly of course, because COVID modeling is far more complicated, but jokingly I told that it is going to reach the same fate, right, like this. So first wave, second wave, first wave, second wave, third wave, fourth wave, like that, and it will decay, die down. Okay, so the virus will die down. And then of course I have another critically damped situation. Critically damped situation is very good. See, s square plus 6s plus 9 equal to 0. When this is equal to 0, then you will see that two roots are overlapping to each other, negative definite, and that ensures that response is like this. So what does it mean? You see, the transient state is very small here. Means this is very good. Why it is very good? You see, if a controller gain is adjusted corresponding to critically damped situation, then if this is where I want my system to go, it will go very quickly. It will go with a lot of delay, and it will also go with delay. But it will go very quickly. That's the reason we like critically damped condition. Okay? So here we can see that instead of step, if this is my forcing function, then the x will be response, system response will be something like, if it is underdamped, okay, so tell me how the system response will be like this. Oops. So you can actually plot this. So you can actually plot if you have this, no, and the solution, because system is underdamped. If it is underdamped, then it will try to catch up this, because this is forcing function. In the steady state, it has to catch this. System is underdamped, then it will try to catch some hesitance, and then it will try to catch again, again like that. So if it is underdamped. If it is critically damped, very good. Then again. Sorry. So this is critically damped, and overdamped, okay. It will take a lot of time to go over there. It will take a lot of time to go over there. A lot of time to go over there. Overdamped situation. So this is another. So you can take any forcing function or excitation, okay, and in the steady state, let it be underdamped, overdamped, critically damped. The response will try to catch the excitation itself. That's why we call the second order system, any controller which follows second order system is asymptotically stable. All the three conditions are stable, but the desirable one is because it is very quick, and the response of the controller will be much faster if it is critically damped condition. If you can design gain parameter and etc., considering a critically damped condition, then the controller will be much better. So with this, I conclude understanding second order system with the help of mass spring damper or LRC circuit or mass spring or LC oscillator. So whatever way you can understand, but it is interesting and important to understand the behavior of a second order system, and I can make sure that when I will discuss control, especially robot control, things will be much more easier for you to understand. And the second order system, of course, has several other areas of application. That's why I wanted that you should have this knowledge, and in the assignments we can give lots of examples, illustrative example, computer assignments. So this can be drawn actually using MATLAB plot with some values of R, zeta. Yeah, and then it is very interesting to see the behavior of the second order system. With this, I conclude, and I wish you all the best. Stay safe. Bye-bye.